in the tail of a comet, which always points away from the sun throughout its orbit, because the comet particles are pushed away from the sun by light pressure. James Maxwell first explained that light consists of transverse electromagnetic waves. Maxwell's laws show how such waves can exert a longitudinal pushing force against matter, and thus they carry linear momentum. Light waves consist of electric and magnetic fields that are transverse to the direction of propagation. When light hits an object, its electric field interacts with an electron in the matter and causes it to move. This is the electron. Here the electric field is drawn vertically, and so is the electron motion labeled V. Such electron motion is responsible for refraction, reflection, and absorption of light by matter. Note the electron motion is also passing through a magnetic field associated with the light labeled B. Such motion through a magnetic field generates a Lorentz force on the charged particle, shown by the green arrow. Maxwell's laws tell us when a light wave with energy U is completely absorbed by matter, such a Lorentz force will impart an impulse of momentum to the matter, where the change in momentum of the matter, delta P, equals U divided by c, the speed of light. Later, with the advent of quantum theory, it was seen that a single photon carries with it an amount of linear momentum equal to Planck's constant times the wave number, or the inverse wavelength. In the late 1960s, many labs were using their new toy, the laser, to explore the nature of light. They tried to measure light momentum by various means, such as reflecting laser pulses off mirrors on torsion balances. But Arthur Ashkin at Bell Labs discovered the simplest and most useful technique for demonstrating light momentum effects. He suspended micron-sized refracting particles inside of a liquid, and when the particles came close to a beam waste from a laser, they were drawn vertically into the waste and expelled out the back side. He explained how the sideways attractive force was in fact a gradient force, sucking the particles toward the most intense part of the light, and how that the force that forced the particles out the back of the beam was a scattering force. In order to make a stable trap and hold a particle stationary, he had to make two counterpropagating laser beams that met in the center and held the particle in a stable position. To understand gradient and scattering forces, consider a refracting sphere that is hit by a photon near its edge, such as this photon with momentum labeled Pn. The particle acts as a lens, and the photon is refracted through an angle theta. It now has a new momentum, P out, and a difference in momentum, delta P, shown here. Since momentum is always conserved, the particle receives an equal but opposite impulse. For a stream of photons hitting the top edge, such force is primarily upward, so it moves the particle toward the intense beam. This is the nature of the gradient force. However, there is a slight tilt to the force vector toward the right, which sends the particle away from the source of photons, hence the so-called scattering force. We can create a simulation to show what Ashkin did and demonstrate it. You can download the simulation from the website. It's called Photons. And indeed, these yellow streaks are the photons of light going by, and the blue circle is a refracting bead. Now, if we do what Ashkin did and get the bead close to the edge, it is sucked into the pencil of light. So that is a gradient force that is sucking it into the intense part, and then it is scattered downstream away from the light. So if I put the bead back in the middle, notice that the momentum, forward momentum of the light is reduced by the bead, and the bead reacts by moving through the water toward the right. Again, in 1986, Ashkin and coworkers made a major advance in the trapping field by demonstrating a stable single-beam optical trap. Here, the bead sits just downstream of the laser focus. Any scattering force from, say, reflected light, and these dotted lines are the reflected light, any scattering force that would push the beam out of the trap is compensated by a refracting effect, where the beams that go through the lens, through the bead, are refracted into a narrow cone forward. This increases their downward momentum, and that, in effect, pulls the trap upwards toward the focus. So there is a balance between the scattering forces and the refracting forces, which increase the forward momentum of the light, and the bead comes to a stable position in the single beam trap. Again, we can demonstrate this using our simulation. Here we see the simulation in which the bead is captured in the single beam trap. And you see it sits just beyond the focus. In fact, we can apply a transverse force to the bead, like this. This little red arrow is the force, and the bead will hold against that force. However, there is a kind of a weak spot in the backside of a single beam trap, and it doesn't take too long before the bead wanders out of it. You can improve this situation if you have a dual beam counterpropagating trap, which we can also simulate. So this is the same total intensity at the focus, but half of the power is in two beams that are counterpropagating. Then if we put the bead back at the center, it stably holds that force, and indeed it will hold a great deal larger force than the single beam trap would do at the same light power. But how can we measure the force exerted by light on a trapped object? Ray photometry gives us such an opportunity. There we measure the angle and brightness of all the rays entering and leaving the trap. Then we can apply trigonometry plus Maxwell's formulas for light momentum to obtain the axial and transverse force acting on the particle. The trick lies in collecting all the exiting light and scoring the rays properly. Here is a picture of a simplified counterpropagating optical trap. It consists of two lasers sending out two beams of light focused by two objective lenses, and they focus at the same spot in the middle. These are polarization optics here, the polarizing beam splitters and quarter wave plates, that ensure that the light from this laser goes through the objective, through the trap, collected by the other side, and onto this position detector called a PSD. Likewise, the light from this laser travels through the system and goes onto this PSD. A PSD is a silicon sensor which is built in such a way that it gives two signals showing the offset and the brightness of the light in the X and the Y direction. These are the properties that we need to score the light momentum flux that is imparted to the light by the object in the trap. Here's a schematic picture of how a trapped object deflects light when it's in the trap. This plane on the left represents the left objective. These dotted lines are the maximum collection angle of the objective, or the numerical aperture. Here is the particle in the trap. And here, in this cone, is a narrow beam of light, which is not filling the objective lens entirely, trapping the object. If there is no force on the object in the trap, then when the light comes out of the right objective, it is centered on the PSD detector. If indeed there is a force, as shown on the right, then that force deflects the object in the trap, and the object refracts the cone of light to be offset on the PSD detector. We can also use that same cone of light principle to detect the forces along the optical axis, the z-axis of the optical trap. So if the laser beam is brought to a focus and traps an object and there is no force on the object along the z-axis, then the cone of light coming out is the same size as when it went in. However, if there's an axial force in the z direction forcing the particle toward the direction from which the light is coming, the cone of light comes out larger. This is a reduction in the momentum along the z-axis of the beam of light. If the particle remains trapped and there is an external force on the particle in the same direction as the light is shining, the momentum of light is increased and the cone comes out smaller. These effects can be used to score the z-axis force on the trapped particle.